This conference will now be recorded.
Thank you. Okay, as I was saying, welcome to the MERLON webinar, to the first webinar we are running in the project. We hope to have a second one and have you again with us. Thank you for joining today, and let's revise now briefly the agenda that we will have for today. Oops, it doesn't move forward. Okay, there you go. So first, this is the welcoming message by me. By the way, I'm Malena Donato from Atos. Then I will give you the floor to my colleague Basso Katatsiki from Hypertech. She will introduce the MERLON and how we are contributing with this research and development project to the transition of energy and contributing to have a greener world, let's say. Then my colleague Miguel Rodriguez, as well from Atos, will explain MERLON from a different perspective, like how people and how the different stakeholders can take advantage and use MERLON. And then we will revise the pilots, the use cases that we have in the project. Our colleague Esteban Pastor from ETRA will present that. Excuse me. And then finally, Katerina Balalaki from Hypertech will do the wrap up of the session, and there will be some spare time for questions and answers. So please try to write down your questions, and at the end, we will give you the opportunity to participate. So we are creating the MERLON framework, really is so people can use the different, energy resources in different ways, and with the thanks to the framework, the idea will be to take advantage of the possibility of using the energy resources. So let's revise that in the next couple of minutes. Before I leave you, these are our social networks. It's like a publicitary post. Try to follow us, and you can Twitter anything anything that you see in this webinar. Feel free to do it, and this is it. So I give the floor to my colleague Basso.
Hello, good morning from my side. I hope you can hear me well. Okay, and I also hope you can see my screen.
Yes.
As Malena mentioned, let us start from an introduction to MERLON project and its overall scope. So with regards to the energy system transition from a centralized structure with inefficient renewable support mechanisms and inadequate regulation in order to foster, let's say, innovation in the energy system and proper cost allocation for balancing, to a decentralized system with distributed generation and demand supply balancing mechanisms, as well as competition and innovation. There is a need for certain progression and certain changes and milestones such as complexity management, energy grid smartening, coordination of flexibility resources that are distributed in the energy system, as well as let's say, system interoperability and information gap bridging are essential. Towards these, let's say, intermediate milestones, MERLON aspires to contribute through the creation of a distributed energy storage optimal planning and sizing tool for operational planning of electricity distribution grids, and through a distributed flexibility optimization platform that is more, let's say, close to real-time operation for local energy system management. MERLON project focuses on integrated modular energy system and local flexibility trading for neural energy islands. The project comprises 13 partners that are from 6 European countries, and the coordinator is Hypertech Energy Labs. It is a 3-year research project that that is planned to be finalized by December 2021. MERLON introduces an integrated, as mentioned before, modular local energy management framework for a holistic operational optimization of local energy systems in the presence of high shares of variable renewable energy sources. The strategic target aims is to contribute to the decarbonization of the EU energy system through the further increase of renewable energy, distributed renewable energy integration, and in parallel increase of security of supply and establishment of cost-efficient solutions against the traditional pathway of grid infrastructure updates. The major stakeholders involved in MERLON framework are DSOs, aggregators, prosumer, and flexibility asset managers. This specific topic will be further elaborated by our colleague Miguel Rodriguez in a consequent time slot of this webinar. And last, their technologies that are involved in the research framework of MERLON are renewable energy sources, battery energy storage systems, EVs, and overall certain local energy system optimization techniques will be explored, including demand response and cross-network synergies. So the MERLON framework is actually deployed and demonstrated in 2 pilot sites in Spain and in Austria. In its pilot sites, which you can see here geographically, a living lab has been set up, including local resources as well as local community there. We can see here an overall, let's say, conceptual presentation of MERLON framework, which is also going to be further detailed in consequent time slots. As an overall comment, we can see that the framework researches different distributed energy sources. It focuses on the prosumer side, on the construction, on the creation of a local flexibility optimization and management framework, and as we can see on the left of the slide. It also creates a tool suite for local aggregators in terms of portfolio of demand flexibility, optimization and management. And last, it creates an integrated local energy optimization tool suite from the point of view of the grid and that supervises, let's say, and coordinates the integrated local energy system. So we can see here from the 2 pilot sites as an example, let's say the structure of the Austrian pilot sites and the several resources that are integrated in MERLON framework. We can see here how they are locally geographically deployed in the area. We can see the aggregators portfolio of demand flexibility, including EVs and prosumer. We can see the PVs that are integrated as distributed renewable energy generators, as well as a central grid-connected battery. The major studies in the area is the battery sizing and planning, as well as the study of the MERLON ILES taking the role of a local DSO, and the study of MERLON ILES taking the role of local aggregator. All the resources are integrated and interconnected through an interoperability framework that ensures communication on the basis of data security and protection. All the framework is also established on the basis of community engagement, which is ensured through living lab activities and workshops that engage the local stakeholders, both in Spain and in Austria. Concluding this presentation, we will focus on the presentation of the expected outcomes as well as the lessons learned from our activities so far. Regarding the expected outcomes of the project overall. First, it is the battery energy storage system integration and interconnection at key network locations of the pilot sites. The optimal coordination of the local flexibility sources that were also presented in the previous slides. The accomplishment of grid balancing through flexibility-induced self-consumption leading to the minimization of curtailment of the PV generators, the contribution to the establishment of actual local energy communities, the establishment of locally organized flexibility markets with transparent market transactions and equally shares of benefits for all stakeholders, the investigation of innovative business models upon the interactions studied above, and the empowerment of local energy stakeholders and the establishment of viable business cases upon the innovative, let's say, local energy system structure. From our research so far, we have selected, let's say, 4 major points which we would like to focus that constitute for us some lessons learned and some challenges that we manage in the end to resolve. First of all is regarding the actual user acceptance in the pilot sites. It is important, let's say, to ensure active engagement of prosumer and the rest of stakeholders and raise local awareness in order to achieve active participation in the research activities. And for that, it was very important the establishment of local living labs in the pilot areas. Second is the importance of the electricity network infrastructure in terms of grid infrastructure and the adequacy of protection measures in order to actually apply the innovative modes of operations that involve, let's say, transition from islanding to on-grid mode. This is a certain challenge that needs to be resolved and investigated. Third, it's the existing regulation that poses, let's say, certain barriers in the experimentation of the innovative business models introduced by the project framework. And last, there are certain connectivity issues and data extractions and retrieval issues from assets that are public, such as public EV charging points, etc., that need a certain permission procedures and certain provisions to be kept in order to, let's say, be proper and aligned with the GDPR measures. So this is all as an initial overview. We will move forward with more detailed focus on the pilot sites, MERLON stakeholders, etc., in the consequent time slots of the webinar.
Thank you so much, Baso. Now let's give the floor to Miguel Rodriguez from Atos.
Hi, everyone. Let me share my screen. Can you see my screen?
Yes, thank you. Go
Okay.
on.
I'm going to present MERLON from the point of view of the different stakeholders. First, the following figure shows the different phases of the energy generation, transmission, distribution, and retail. In the generation part, we can find new actors defined by the USEF. This is the Universal Smart Energy Framework. These new stakeholders will be addressed later in MERLON. First, the prosumer. Prosumer can be regarded as an end user that no longer only consumes energy, but also produces energy. USEF does not distinguish between residential and end users, small and medium-sized enterprises, or industrial users. They are all referred to as prosumers. In this test, we also use the term prosumer for end users that have controllable assets, active demand and supply, and are thereby capable of offering a certain management of their assets that is called flexibility. Next, the energy communities can be included in the category of prosumers. They are usually organized as local cooperatives and can participate in the local market in a limited manner. Next, the microgrid operator. The role of this stakeholder and also the DSO is making microgrids an integrated part of the electricity distribution system of the future. In the retail part, we have the following stakeholders. Trader, which buys energy from market parties and resells to other market parties on the wholesale market, either directly on a bilateral basis or via the energy exchange. Aggregator. The aggregator is another important stakeholder. But first of all, I must introduce the concept of ADS. ADS means active demand and supply, which represents all types of systems that either demand energy or supply energy, which can be actively controlled. This enables the ADS device to respond to price and other signals from the aggregator, and to provide flexibility to other markets via the aggregator. Therefore, the role of the aggregator is to accumulate flexibility from prosumers and their active demand and supply, and sell it to the supplier or the DSO or the TSO. Finally, the ESCO, the energy service company, offers auxiliary energy-related service to prosumers. These services include insight services, energy optimization services, and services such as the remote maintenance of ADS assets. If the supplier of DSO is applying implicit demand response through, for example, time of use of tariffs, the ESCO can provide energy optimization services based on tariffs. Unlike the role of aggregator, the ESCO is not active on wholesale or balancing market. Citizens are a key element in the energy transition. Therefore, the objective of the European Union is to place the citizens in the center, enabling to trade with their renewable energy. Therefore, the purpose is that the citizen is a main actor turning him into a prosumer. Citizens can benefit from this, for example, by reducing their bills and protecting from economic vulnerabilities. To achieve this, it is required that the citizens can access to the new technologies, for example, blockchain, which can be used to provide confidence to prosumers when transacting with their energy. The following figure shows the different components, functionalities, and energy resources that are managed in MERLON from the point of view of the stakeholders. First, the aggregator manages the global flexibility manager with the following functionalities: optimization and management by the use of flexibility analysis, forecasting, segmentation, and clustering. The ILS, this is the integrated local energy system, is managed by the DSO with the following functionalities: demand and supply flexibility forecast, high-level dispatch scheduling, monitoring and flexibility dispatch for local energy optimization. Also, MERLON can manage different energy resources like cogeneration, electric vehicles, storage, renewables, and commercial industrial. The prosumer is located in the households with the following functionalities: local flexibility optimization management, virtual thermal energy storage, flexibility profiling analysis and forecasting, monitoring and control DSS. Finally, in the center of this, we have the flexibility pooling and sharing marketplace that enables the energy transactions between the local stakeholders. The previous slides led us to define the following roles in MERLON. In the center, we have the MERLON roles, and in orange, we have the USEF roles. MERLON manages prosumers as it is defined in USEF. The association is direct. Regarding the local aggregator, this operates inside the energy community and can be played by following the USEF roles: aggregator, DSO, and retailer. Also, the instance aggregator or external aggregator is the role in MERLON that uses the functionality scalability to aggregate several integrated local energy systems or energy communities. ILSN manager operates in the whole energy community and corresponds to the role of the DSO. ILSN manager shows a holistic view of the ILS, integrated local energy system, and has the following functionalities: to show the status of the ILSM and to provide a manual intervention to solve real-time issues. And this is all from the perspective of the stakeholders in MERLON.
Thank you, Miguel. And let's leave now the floor to Esteban Pastor from ETRA Group, please.
Yes, let me share my screen.
Yes, please.
Okay. So you should be able to see my screen now in presentation mode.
Yes, we see it.
Okay.
Thank you.
Okay, perfect. So in this session, what we are going to introduce and to present is basically the MERLON pilot sites, in which the different tools that have been presented and the different the environment that has been presented by my colleagues before is actually being put into the ground and being demonstrated. So in MERLON, there are two pilot sites in which we are demonstrating and going to keep demonstrating the solutions developed. which is the first one in Austria, the Strem area, and then the second one in Spain, in the Crevillent town. So let's go through them. The first pilot site that we're going to present is the Austrian pilot site, as I was saying, in the Strem and Gusing area. We can see the area here, which is 12 kilometers wide, 12 times 6.5 kilometers wide. And we have two different areas or sub-areas, let's say, or subsections of demonstration. The first one is the Gusing town, and the second one is the Strem town. So now we will introduce which are the differences and what each one of the areas does. So basically, if you can see the pointer now, we have three differentiated areas. The area A, in which both the Gusing and the Strem pilot sites, pilot sites or area sites are included. For this area, the main interest is to raise awareness again among the citizens and to gather information to feed the tools and to feed the platform of the project to better be able to manage the energy systems and the energy assets that are included in the project. Then we have in one of these two sub areas, we have the area B, which is the town of Strem that you can see here. For this area, we are starting to include engagement, active engagement of consumers, which basically it is not only about gathering information, but also about interacting with them in an energy perspective. And then the area C is where which is a small part of the Strem town, or where another part of the Strem town is where the consumers, the customers, have actually an active participation in the market and in the electricity and the energy environment, we could say. So these are the three different areas in which three different levels of actuation and three different levels of user engagement are deployed and are being tested. So in this Austrian pilot site, there are, for instance, currently more than 3.1 megawatt of renewable energy peak power generation already integrated and already being managed and monitored by the different project tools. Going through them, or through the most important ones, for instance, we have a biogas combined heat and power plant, which is located in this area C that we were seeing before, which has 500 kilowatt peak of renewable generation. And we have several different large-scale PV plants. You can see them selected here or pointed out here with these photovoltaic panels icons. So for these ones, we have a 1 megawatt PV plant, which is actually happening to deploy an extension of another megawatt peak power, which is basically doubling the power that it currently has, up to 2 megawatt of renewable photovoltaic power. We have another PV plant, which is 0.34 megawatt peak, which is also seeing another extension, which is bringing it to almost half a megawatt, or to more than half a megawatt of peak power. We have a 170 kilowatt peak photovoltaic installation. We have another 30 kilowatt peak photovoltaic installation and another 25 kilowatt peak. So these are the not bulk PV plants, but distributed PV plants, which already have significant power injected into the grid. But it is not only this, the generation that we have in the pilot, but also, as you can see here, there are several icons for different users, because there are many households with PVs, which basically represent the prosumers in the pilot. Bringing all that together and adding all that up, we end up with this more than 3 megawatt peak of renewable power generation in the pilot site. If we move from renewable generation to renewable storage, this area that you can see here from a Google Maps screenshot is it's located in the smallest area that we were showing before, the area C, and here there is a section of the town that has been selected in order to deploy the battery storage system. So basically, in this part, we have the land to deploy the battery electric storage system, and we also have a local renewable energy installation, photovoltaic, attached to it. So for this battery electric storage system that is going to be deployed, we will have direct local renewable energy generation that will be feeding this battery when there is excess energy, so that we can minimize the losses in the grid. But well, of course, as the battery is connected to the grid, the excess from the rest of PV plants that were mentioned before, as well as from the rest of renewable energy generation, is also coming there. So it is the battery of the energy community in the Austrian pilot site of MERLON. This battery unit has, for instance, 250 kilowatt installation, kilowatt peak power, and it has 250 kilowatt hour of capacity, which means that in case of an outage or in case of a fault, a problem in the grid, and then the battery should be the one providing the whole power to the area, to the energy community. If there was a peak of 250 kilowatt demand, the battery could be delivering this energy for a whole hour until the technicians of the DSO could actually solve the problem. So the area of this MERLON pilot site would not be without energy supply. For that, this battery has an island mode operator, which has always a reserve power, just in case this situation is given at certain points, so that the community doesn't run without electricity at any point. Moving now to the other pilot site, the Spanish pilot site. This pilot site is located in a district called El Realengo, which is a district that belongs to the Crevillent town, and it is located 2 kilometers away from the downtown. So basically, in this area, there are more than 320 inhabitants with 58 consumption points. And something which is very particular to it, that you can see here in the pictures, that this area inside the red box is the demonstration area, where the consumers are located. But a very significant characteristic of this area is that it is right next to a bulk PV power plant, which has more than 13 megawatt installed power, which was built in 2007, and back then it was one of the biggest photovoltaic plants in Spain. And that means that normally this area is being provided with full renewable energy local generation. Some things that make this area interesting in order to demonstrate and deploy the MERLON solutions is that basically the area is fed from the grid by one single line, which is this red line that you can see here. So basically, if there is any fault in the line, the whole area would be running by itself. So for that is why the MERLON systems, the MERLON tools are going to help manage the energy feeding to the end consumers if any fault appears. So as I was saying, as there is only one line feeding the area, the problems cannot only be a cut in the line, but also congestions. I mean, the district could be asking for more energy than the line could deliver. So in order to solve this, well, there are several different options. The first one is to add more lines to the feed of the district. But well, this is a rather expensive and inefficient manner of solving the problem. Or we can act over the demand side of the energy demand, not only from the side of the consumers, but also from the side of the management of the grid in terms of energy storage. And this is where the MERLON solutions come up and help solving any eventual issue that may appear. So for that, the MERLON project is going to deploy an energy management environment, let's say, in the Spanish pilot site, which is meant not only to be an energy management tool for the DSO and for the local cooperative, but also to be a key point, a key point for the community to gather around. So here you can see that this is what is expected to be the central point of the Spanish pilot site, with the battery included there, with photovoltaic generation, with this electric EV charging point, and also, of course, with all the prosumers included in the project to be feeding also the system and the community. So for this battery storage unit, as we were also mentioning the battery that is going to be deployed in the other pilot site, here we're going to do the same, which is the asset that is going to provide the bigger flexibility and the biggest, let's say, adaptability to the energy needs of both the consumers and the generation side. So this battery unit has a 100 kilowatt peak power, and it also has 250 usable kilowatt hour, which means the capacity. So meaning that this battery could be delivering 100 kilowatts to the community during 2.5 hours without running out of power, of energy. Again, as in the other pilot site, the battery is provided with an island mode operation that in case of any fault, in this case not a congestion fault that limits the energy that can enter into the district, but rather an actual blackout fault in the line. So this battery could also perform a self microgrid operation in order to run the energy needs of the district until the technical people from the DSO and from the cooperative could actually solve the problem in the line. So as you can see, these have been the two approaches in which we are going to demonstrate the MERLON solutions. And well, if you have any questions, we'll be happy to answer them.
Thank you, Esteban. So let's give the floor now to Katharina from Hypertech, that she will wrap up the webinar. We are just on time, so go on, Katharina, please. And at the end, as we have said at the beginning, we will have some time for questions.
So thank you, Marlena. Hello, everybody. I'm Katerina Valalaki from Hypertech, and I'm just going to wrap up what we have discussed already by my colleagues in MERLON. So what is the actual contribution of MERLON in the energy transition era? The MERLON solution came up as an idea to solve some problems and issues identified in the EU electricity system. Indeed, the increase of variable and intermittent renewable energy resources that has stochastic output may result in grid stresses. And this is coupled with still unstable regulatory framework in the most EU countries. If we couple this with the non-viable market offerings for small consumers, this framework already existing in Europe makes the energy stakeholder just passive energy actors. So we have identified the need for large capacity decentralized storage combined with additional technologies for local energy system optimization, like, for example, demand response and electric vehicles. This could support the renewable generation, and our target is to minimize the curtailment of renewable generation. While if we couple this with fair contractual relationships, and we manage to overcome the minimum sizing of bids, we will be able to contribute in the transformation of local stakeholders to active energy players. So in this framework, MERLON solution comes to provide innovative business models where actually energy communities take the role of DSO or the aggregator, what we call in MERLON aggregator of aggregators, provides a battery energy storage system with grid forming capabilities in order to support even off-grid operation. Provide a bundle of technologies for modifying demand without any violation in the comfort of the users. And all these are nicely integrated in a holistic way in order to coordinate in an optimal way the local flexibility resources that exist in the local energy system. So where are we now, where we would like to go, and how MERLON bridges this gap? As mentioned before, the today's regulation and technology is characterized by ill-designed end-user tariffs, inadequate regulations for procurement and cost allocation for balancing, and inefficient mechanism to support renewable energy resources integration. What we need to achieve in the near future is to go to, let's say, advanced regulation and technology case where we will speak about economies of scale and scope, while the EU electricity system will mainly focus on competition and innovation. So what we have now is the transition phase where we need to engage and coordinate power system agents, manage the complexity introduced through the deployment of different technological advancements and the deployment of automation technologies in order to close these information gaps. Here, MERLON comes to provide advanced technical and interoperable solutions and effective business models in order to contribute to this energy transition era. Focusing a little bit in the business models, MERLON project actually is composed of a number of partners ranging from industries and small medium enterprises, research institutes and universities, public sector and citizens. And all together, we're trying to define and realize the MERLON business models. In this value chain, actually at the bottom of the value chain are the citizens themselves. In MERLON, customers of our energy cooperatives in Austria and Spain assume this role. And actually, they are the prosumers that are going to provide their flexibility without any disturbance in their comfort. On the other side, we have the actual energy cooperatives that assume the role of local aggregator, and their aim is to gather the flexibility for the different prosumer and valorize it in order to provide different services to the TSO and the DSO. And at the upper level of this value chain, we have the LSM manager, which is actually the one who tries to coordinate in an optimal way the whole integrated local energy system. It utilizes the flexibility, the aggregated flexibility provided by the local aggregators in order to perform constraint management or to provide different balancing services to the upstream network. The business models themselves and the technological advancements that are provided in MERLON will be demonstrated in 2 pilot sites, one in Spain and one in Austria. Both pilot sites include a number of flexibility resources ranging from loads at prosumer level to renewable energy resources like photovoltaics and the integration of electric vehicles, while a key point is the installation, the procurement, installation, and integration of battery energy storage systems that will be purchased within the MERLON framework. One of the key activities of MERLON that actually enable the contribution in this transition era is the activities and the support of the BRIDGE initiative. BRIDGE is actually an initiative initiated by the European Commission that unites projects in the Horizon 2020 framework as regards smart grid, energy storage, islands, and digitalization area. So BRIDGE actually fosters continuous knowledge sharing and tries to gather conclusions and recommendations with a single voice. To this end, BRIDGE has structured 4 different working groups, namely data management, regulation, business models, and customer engagement. And actually, MERLON actively participates in BRIDGE by dedicated representatives of our consortium that contribute to the BRIDGE working groups, participate in BRIDGE General Assembly meetings. MERLON also provides continuous feedback by filling in questionnaires or participate in surveys, organizes workshops with other BRIDGE projects, and finally participating in the actual process of the planning and organization of next steps in the various working groups of BRIDGE. So that's all from my side, and I think that with this we summarize everything about the MERLON project. We are happy to answer any question that you may have.
Thank you, Katerina. Yes, in fact, you can directly open the micro and ask your question. No, there are no further questions. Okay, then it seems you guys did pretty well. Yes, go on, Rafael, right? Yes.
Hi, my name is Rafael Stott from Germany. What is the dynamic you manage the energy? Is that seconds, is that minutes, or a quarter of an hour? Because if you do an island mode, you should have a quite high dynamic of managing the system, right?
Right, so I think maybe Basso can answer the questions on even Anthony's, please.
Okay, so for now we have, let's say, some different demonstration scenarios that we are going to deploy and show in each pilot site, where these scenarios generally range from operational planning, where actually the scheduling of the units takes place on a day-ahead basis, and there we have half-hourly set points defined. So this is the larger, let's say, time granularity that we use on planning. And then we have intraday scenarios where we go to a minute based granularity. So in intraday scenarios, we have immediate intervention. Either this would be islanding or it would be immediate, I mean, real-time intervention from the battery in order to correct, let's say, local faults arriving. And then consequently, we will have the revision of operational set points of the flexibility resources for 1 hour ahead on a minute basis. So actually, to conclude, let's say, after describing these different, let's say, time ranges, just to conclude, we have a range, let's say, of possibilities depending on the scenario that each time we will demonstrate. So this ranges from minute and minute-based, let's say, scheduling of the units to quarter of an hour and half an hour based scheduling of the units. Other than that, for islanding, for example, the battery will take immediate actions. This is an emergency, let's say, scenario where we have sub-minute responses.
Thank you,
Thanks.
Basso.
So that is, it is actually modular. It is actually, scalable, the responsiveness of the tools.
Yeah, makes sense. One more question. What kind of battery you are using? What technique?
For the, okay, I will take over this answer as a continuation of the previous one, if you don't
Yes,
mind.
go on.
So actually, in the two pilot sites, a bunch of specifications and in terms of size and behavior of each battery were defined in the project work packages, and they are now in the process of purchasing. So up to now, and according to the studies, I think that in both pilot sites, lithium-ion technology has been chosen because it actually has two advantages. It can operate in a partial state of charge, so it can it doesn't need to be fully charged, so it can serve both charging and discharging scenarios that is essential for balancing. And second, it has a very straightforward, let's say, charge and discharge curve, charge and discharge characteristics. So it has high power and energy density. It has beneficial to our demonstration scenarios and pilot site requirements behavior, charge and discharge behavior, and last, can operate in partial state of charge. So it was concluded that this technology served the requirements of the pilot site. Regarding the size, beyond the technology per se, the sizes were different in each pilot site. As it was presented, for the Spanish pilot site, a battery that was energy intensive and could provide autonomy was chosen. For the Austrian pilot site, more emphasis, let's say, in capacity-related services, power-related and capacity-related services was given. So it was more high power, or let's say equally power and energy intensive, the battery. The first state was 250 kilowatt and 250 kilowatt hours approximately. And for the second pilot site was 100 kilowatts, 250 kilowatt hours for the Spanish pilot site. So this depended actually on the applicable business cases and demonstration scenarios per pilot sites, the choice of size.
Okay, thank you. Are there any other questions or comments that you want to share with us?
Hi, this is Pablo from Energía. In the presentation, I've seen that in Spain, it was written that there was some congestions in the line that goes from the city to the neighborhood, and there was some problems to increase the renewable energy sources. Was that right or not?
I think, thank you for your question, Pablo. I think Esteban, you can answer this question, please.
Yeah, well, actually, well, yeah, the thing in congestion is that this neighborhood or sub-district is connected to the rest of the grid through one line and one transformer. So there might appear congestions there, which are going to be solved with the integration of this battery inside the district. So the storage will be done inside the district, but the problem of not having enough renewable energy is not a thing here. Here the renewable share of that district or area is quite high. So
how much capacity do you have there in PV installations?
Well, the installation, the PV plant, which is connected right next to the district, has 13.5 megawatt power, which of course is feeding not only the district but the grid itself.
Okay. Thank you.
Thank you. So are there any more questions? If not, we can close the webinar. Thank you for attending the first MERLON webinar, and we keep in touch.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.
Thank you very much.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.